model. So the Anova is simply going to ask the question whether or not there are any differences anywhere at all between our groups. So unlike a t-test that specifically compares only 2 groups at a time, the Anova is going to compare all 4 groups together simultaneously. Now, this means we get a single p-value, and therefore we don't have the issue of inflating type 1 error like we did with t-tests, but it does come with a technicality. This one p-value will highlight if there is a difference anywhere between our groups. The catch? It doesn't tell us where that difference lies. It effectively says, yeah, something's happening somewhere, but you have to go work and figure it out. We're not going to talk about how do you figure that out today. That's next week, and I don't want to have any spoilers. So let's just look at the Anova today, get ourselves familiar with it, and then we'll look at what do we do afterwards next week. So the null hypothesis of an Anova is just an extension on the t-test null hypothesis. So for the t-test, it was the dependent variable mean for group 1 equals the mean for group 2. And Anova, it's the dependent variable mean of group 1 equals that of group 2 equals that of group 3, all the way through to your last group, and they all, when that difference all equals 0. So all we're saying is if I was to calculate the difference of all my groups, they would equal 0. But otherwise their means would be identical. Now what this means, if you think about this, if I was to rewrite the t-test null hypothesis, mean 1 equals mean 2, the t-test null hypothesis is actually just the first section of the Anova null hypothesis. And this is an important distinction to make because what it means is you can actually run t-tests in Anova. So t-tests are just a special case of Anova. When you have 2 groups, the math simplifies and we get a t-statistic. But when you have more than 2 groups, you can use Anova. It's a little bit more complicated. But nevertheless, if you put 2 groups into an Anova, you get the exact same results as if you ran it through the t-test. They're the same thing. So the syntax for Anova is Anova dv iv. Now, later on we'll talk about having more than one iv, but you can have as many as you like here. For this week, we're looking at just one. And Statter expects a single dv, so that's how it knows that this is the dv and everything else must be ivs. So what I can see is I have 80 observations. My r squared is 0.09, and this tells me that approximately 9% or 9.42% of the variance in sperm count is accounted for by the number of soy meals consumed per week. You don't need to worry about these other 2 numbers for now. I then see 3 different rows. I see model, S-meal, residual, and underneath I see a 4th row called total. And what I notice for now is that model and S-meal are the same. In a couple of weeks' time, when we start working with 2-way Anovas where we have more than one IV, we'll start to see this model line change. But for now, it's going to just be the same as whatever the other IV is, whatever our IV is. We're not going into the technicalities of how partial SS are calculated, nor are we going into mean sums of squares. We'll do some very basic stuff, but nothing too complicated. But what I did want to talk about was degrees of freedom. And then we'll also talk about F and what P is. Now, what these numbers represent, so if we ignore the model line and we look at these 3 values here, S-meal, residual, and total. Total sums of squares represents all of the reasons why a person got the score they did. So if we think back to regression, I used the Venn diagrams. I said inside this circle is all the reasons why a person got the dependent variable score they did. And that's very much the case with Anova as well. And then our sums of squares for our IV is the amount of variance in the DV that's accounted for by the IV. And then the residual term is everything else. This is expressed in a unit called sums of squares. And so what we see is S-meal has 135 sums of squares, whereas residual has 1,298. If I add these 2 together, I'll get 1,433. Now, degrees of freedom. Degrees of freedom is this concept about how many numbers do I need to know to predict a particular mean. And the best way to describe this is actually not so much how many numbers do I need to know to predict a mean, but if I know the mean, how many numbers do I need to know? So let's say we have 4 groups. And I know that their mean equals 10. I know that if I was to add all of these up and divide them by 4, I will get 10. Now, I would then ask the question for degrees of freedom. For this first number here, how many values could I have? So for this first number, how many values could it be without affecting my mean of 10? And the answer is, it can be as many values as it likes. The same is going to be true of my second value. It can take any value it wants. And the same with my third. But my last value, there is only one possible value that it could take. And so if I know what these first 3 scores are, I have to know that tells me what this value will be. It can only have one score, and it's dictated by the other 3. What this means is that these 3 scores, if we call these scores degrees, then if I have 4 groups, 3 degrees have the freedom to take any value they like. So in other words, I have 3 degrees of freedom. If we change it up, let's say I have 3 groups now. Let's say it equals 20. Again, this degree, or this group, could have any score that it likes. The second degree, the same thing. The third degree, though, will be locked in. And so now I have 2 degrees of freedom. 2 degrees that have the freedom to be any value they like. So when I'm talking about the degrees of freedom for my independent variable, it's about how many groups of my independent variable can have any value they like without affecting the mean. So if I have 4 groups like I do in this study, I'll have 3 degrees of freedom. Now, if you prefer mathematics, this is effectively the same thing as saying degrees of freedom between, or for my IV, is k minus 1, where k equals number of levels of IV. So I have 4 levels, so k equals 4. 4 minus 1 equals 3. Now what about the residuals degrees of freedom? It's 76. So the residuals degrees of freedom is asking the question, how many people in each group can have any value they like without affecting the group mean? So let's say I had 3 groups, group 1, group 2, group 3, and each of those had 4 people. I would know that for group 1, 3 people could have any score they like. For group 2, 3 people could have any score they like. And for group 3, 3 people could have any score they like without affecting that group's mean. So that means group 1 has 3 degrees of freedom, group 2 has 3 degrees of freedom, and group 3 has 3 degrees of freedom. So across my 3 groups, there are 9 degrees of freedom. Now we have 4 groups, and we have a total sample size of 80 with 20 people in each group. I'm not going to draw out 20 lines, but you can kind of already guess, right? For each group, it's going to be the number of people in that group, little n, minus 1. So if I have 20 people, minus 1 means I'm going to have 19 degrees of freedom in each group. 19, 19, 19, and 19. Now if I was to add this up, 19 times 4, I get 76. And if I go back to my output, I can see I have 76 here. So it's all about asking how many degrees of freedom are there in each group, and then adding those groups up. Now my total is simply how many people across my entire study can have as many values as they like without affecting the mean for my entire study. And that is effectively your entire sample size minus 1, 80 minus 1, in this case gives us 79. So if I was to write up those formulas, df within is going to be k times n minus 1. So n minus 1, the little n, so if we do this again, where k equals the number of levels of the IV, and n equals sample size in each group. And note I'm using little n. However, the total degrees of freedom is big N minus 1, where big N equals total sample size. So little n is the sample size per group, big N is the total sample size of the whole study. Okay. To get our mean sums of squares, all we're doing is we take our partial sums of squares and we divide it by our degrees of freedom. 135 and a bit divided by 3 gives us approximately 45, and so on. For the residual, 1298 divided by 76 gives us about 17. Now, I said before that if I add my two sums of squares for my IV and my residual, I get my total. This is true of my degrees of freedom. I can always add these two and I can get my total, which means I only need to know 2 of these scores to know the third. The same cannot be said for mean sums of squares for this column here. If I add 45 and 17, I most certainly do not get 18. Stat is actually one of the few stats programs that will actually give you a total mean sums of squares, because conceptually it doesn't make sense to talk about a total mean. So normally all you would see is these two values, and they're not additive. You can't add them up. Our F statistic takes our mean sums of squares for the IV and divides it by the residual. So in this case, 45 divided by 17 and a bit gives me 2.64. So if I was to just take a moment, I'm just going to very quickly copy this and put it into Paint. What I want to show you is just all those formulas I was talking about. So if I divide this number here by this number here, I'm going to get 45. Similarly, I can do that down for my residual. And then if I divide 45 by 17, I'm going to get 2.64. Now it does work the other way as well. 45 times 3, that's a terrible times sign. 45 times 3 is going to give me 135 and a bit, and similarly 17 times 76 gives me 1,298 and a bit. Now, where does this 2.64 take us? So this 2.64 simply represents the ratio of mean sums of squares of our IV to the residual, which effectively means if we talk about a one-on-one basis, or as close to one-on-one as we can get, our IV is actually a pretty good predictor to some extent. And we can see this because our F is greater than 1. If our F equaled 1, then that means that the mean sums of squares score here is exactly the same as the residual. In other words, we would be no better off than guessing whether or not soy meals actually affected sperm count. So with F being greater than 1, it means that there's a chance that this might be significant. We then have a p-value attached to this. Now p-value is 0.0558. So this is what we call marginally significant. It's almost there, but not quite. Now, how is this p-value coming about? What's its relationship with F? Behind the scenes, what we have is, this is what we will call an obtained F. This is the F that we got when we calculated our Anova. And this is being compared to a critical F that comes from an F table. And the critical F is the F that we would get if we had these degrees of freedom and the null hypothesis was true. If our F is larger than the critical F, then it's a significant effect. Statter is very smart and can calculate the exact level of significance. I bring that up now, although we're not looking at F-tables today, and later weeks we will be looking at F-tables, so I wanted to bring that to your attention now. Despite all of this, we could have taken a different approach to calculate our ANOVA. We could have used the one-way command. So here, one-way, dv, iv, and then we can use the tabulate command afterwards. And if we did this, we'd actually get univariate, so our means and standard deviations. We get our ANOVA table. We'd also get the Bartlett's test, and the Bartlett's test is similar to Levene, so it's equal variance. It produces a different p-value because it is technically a different test. Generally speaking, we consider Levene's to be a more appropriate test than Bartlett's. The other problem with using the one-way command is you don't get your R squared, and you still don't get your skewness and kurtosis, so you still have to go through all the other steps anyway, but if you're trying to speed through it, this is an alternative. Personally, I don't recommend speeding through anything when it comes to stats, but everyone's different. So how do we interpret this p-value? What this is telling us is that the amount of sperm that a man has does seem to differ depending on the number of soy meals that they consume. However, we don't know where that difference lies. We don't know if it's between no soy and 1, or 4, or 7, or anything in between. We simply know that there is a difference somewhere. So next week we're going to start exploring how do we find this difference. Okay, I'll see you then.